Good morning. My name is Ralf Muehlen. I work for the Internet Archive. We are probably best known for the Wayback Machine, where we store 400 billion web objects going back all the way to 1996. But we're also archiving a lot of other content. For instance, we are digitizing about 1,500 books in 35 scan centers on 4 continents, so 1,500 books per day. And we're making them available either for borrowing or for outright downloading. We are also one of the newest big collections is the television collection. We've been recording for about 12 years. We were recording when 9/11 happened, and we have those, but we've expanded it lately. And the idea is to make television searchable and quotable. And a few years back, we came across this building and thought, this looks exactly like our logo. It's fate, we gotta have it. So my task was to turn this church from 1923 into a modern data center and office. And we did that, wasn't quite easy. And then one day we had a giant party. We had it was in the middle of a 2-day conference. We had about 500 people in the house. Donald Knuth, computer science pioneer, was so kind to play the organ for us. And then all of a sudden, it's dark. The organ doesn't play, the lights are out, power's lost, the data center's down, the website is down. And we actually saved the evening by running extension cords from the neighboring building and just powering one projector and a laptop. That led to some head scratching, and this is what started me on this whole adventure and looking into things. So the ultimate cause of that outage was that the utility had not provided as much power as the building was built out for. So we found 800 amps in the building, thought, oh great, we'll never exceed that. And then it turned out in the street, the transformer had only 320 amps. And if you ever want to see scared electricians, it was funny when they put the breaker on the transformer in the street and they had like a giant hook, like, you know, it's almost comical, like the kind of hook that you pull somebody off the stage with. So we didn't see that coming. We were flying blind, and we needed to make some changes. This is the Austin, Texas style solution to an uninterruptible power supply. Might not protect against all outages. So we were looking around, what is available, what do we already have, and how can we get a little more situational awareness. And the situation wasn't all that great. So this is, we had a particular model of power strip that we initially selected for cheapness. It wasn't exactly cheap, but the thing that really bit us a few times is there was an embedded controller in it that you can then talk to get a power, basically an amperage measurement in real time. But when the power fails, or if you deploy a new rack, well, it asks for DHCP lease exactly once while your smart switch is still booting. So if you run a data center with dumb switches, this is the power strip for you. And this is not a power strip used like, you know, elsewhere in the world for 240 volt. This is specifically designed for North American data centers. It's made for 208 volts. It has a NEMA 5L30 connector. The only people buying this are data center ones. And I have no real explanation why this product exists the way it is, right? There is a free stack of the implementation for DH client. Thank you, ISC. Somebody re-implemented DHCP badly, and you see this over and over in these embedded kind of things where people are either not aware that there's an open source implementation, or it's very outdated and very clunky. Another example is an embedded fan controller. Luckily it spoke SNMP, but that was also the only thing it spoke. And you can use those and script them together, but I was offended by you need to write a 0 to turn the fan on and a 1 to turn it off. You have complete freedom on how to design this SNMP stack, and you do this, and I wonder, like, how does this happen? Then there are smart meters. That's kind of like a solution that would work, right? It is real time, it's networked on a wireless network on its own frequency, probably licensed. It is likely to be accurate because somebody is certifying these things. And the best thing is somebody else already installed it, so it's already there. But unfortunately, you can't plug into it. There's no data port on it. There's no API. There is a website that where I live in San Francisco. It works for me in my home, but as a commercial user, the website is broken. So I can't even screen scrape the website. I found out later that all of these power meters have a infrared LED that blinks for every unit of energy consumed. What that unit is seems to vary, but think of it like a kilowatt hour. It blinks occasionally. Of course, you would never know because it's infrared, and there are things you can clamp on top of it that will count those. So this is kind of a lost opportunity in a sense, right? This data is there. It would be great if we all had access to that in a scriptable fashion. So there's a lot of movement happening now with embedded boards, right? A lot of the stuff that I'm talking about today would have been possible 10 years ago, but there's some fundamental changes now happening. There's a lot of new embedded boards available, most notably the Arduino Yun, or Yan, that have a built-in Ethernet port now, or the Raspberry Pi, but there's a whole variety of them. And at the same time, the consumer Internet of Things is taking off. There are very slick products that are just super easy to use, very slick, but also often proprietary islands that it is hard to integrate with. So you get a whole variety of choices there, and the choices range from you can solder a solution yourself, or you can go to the cloud and program against the cloud if it's open enough. It also ranges from openness to closeness very much. But what has changed is just the availability of so many options now. It's kind of a new revolution with a lot of momentum happening that gives us new options. And you can pick and choose kind of what you're comfortable with, low end, high end, slick, not slick. There's a variety. And for me, the change was like, oh, doesn't feel like a grind anymore. This is actually becoming fun. So my first adventure was like, I wanted to have a real-time power meter for the entire data center that I could rely on. I didn't need 100% accuracy, but it needed to be roughly in the same ballpark. And also important, I didn't want to kill myself. You have to be a little careful doing that. I initially thought, oh, since we were upgrading, the power utility was upgrading the transformer in the street, that would be a great opportunity to get in there. In the end, it turned out they did it after they installed the new lines. So that can actually be safely done. This is what it is. There is a ferrite core. Think of it like kind of like a magnet that can be opened, so you can slip it around an existing power line. You need to grab each face separately because otherwise the magnetic field cancels each other out. The way this works is by induction. So a small current is induced that is proportional to the real current going through the cord. And I kind of went off on the deep end there a little because I thought, okay, that current is proportional, so I just put a burden resistor on and I can measure it. Then I realized, oh, it's AC, so I need to rectify it. So I built a rectifier out of 4 capacitors and 4 resistors. And then I realized, oh, I need to calculate the root mean square to make this meaningful. And then I realized that my sensor hub already had that built in, so I didn't have to do the math. I threw away all the rectifier stuff and basically just took these wires and plugged it right in. And then I just needed to do a little calibration to figure that out. But the math for that was very, very easy. This is what this looks like. This is the power lines coming in. I clamp one around all 3 phases and not the ground, and then I put it in a nice looking box. We happen to have a surplus of external hard drives after the flood in Thailand. And this is what the first graphs kind of look like. You can kind of see the ups and downs for day and night. By the way, you might be wondering, why is one phase off? Well, this is what is called split phase in North America. If you never heard of that, if you're from Europe or Asia, be glad. It's a kind of weird system. It basically means that any normal consumer like laptops and light bulbs or so are on the yellow and the blue phase and not on the green phase. So I anticipated that the electricity goes up and down in the building as humans walk in. I didn't think it was quite so much, so this is like 5 kilowatts or so. And on the bottom, on the green line, you can kind of see two compute tasks. This is a kind of MapReduce style computation where a task gets deployed on many machines in a cluster. They compute and finish at different times and then combine the whole thing. I was vaguely aware of these. I was surprised by the energy impact. I didn't know that. So this was kind of like a, aha, here's something interesting to see. And there's opportunities there. If you move the task at night, you have two advantages. It's cooler at night, especially for us not using air conditioning. And if you're at a certain size with a data center, it is advantageous to get a pricing plan that takes the time of day into account. So there's an opportunity there to move the compute task to run at night when the electricity is cheaper. I started with that, and then I thought, what else can I do? So a lot of sensors are commercially available: temperature, moisture, some of the smaller amp meters that you can clamp around. There's also power strips that you can query directly. One thing that I was missing was a kind of airflow meter. I first had a little propeller that was always fall off. Then I used a piece of paper that works really well. It indicates in which direction the air is flowing. Very fail-safe, very cheap, but you can't see it remotely. And then I looked around what's available. Many sensors are built for industrial users, like if you have like your chemical plant or your uranium enrichment plants. These sensors are extremely expensive and extremely accurate. And what I needed to know was basically, is the air flowing or not, and in which direction maybe, and see if there's a trend over time, say if the airflow gradually gets lower over the course of a month, maybe my filters need to be replaced. So I found a relatively cheap sensor, bought it on eBay, put in a burden resistor, and then I could measure it. And that's kind of a principle you can apply if you find any sensor out there. Usually all you need to do is get it into the range what your sensor hub can take as an input, and then do a little calibration. This is chiseled in the lobby of the Humboldt University in Berlin. So far I've done only measurements, and then I thought, okay, I wanna actually do something, namely turning fans on and off. And the idea would be run the fans only as you need, overbuild it in case some of them fail, and change that. And that is a very scary step. So my recommendation is first get started with measuring things, and then maybe turn a light bulb on to simulate how you would turn on a fan, and then get comfortable with it. Another important step is to not disenfranchise staff that is already there. No matter how good your sensor network is and how good your situational awareness is, you will never beat the human who is in the building at the time. So for a lot of these things, we put manual overrides in so they can force fans on and off and then return it to normal operation. As a side note, it was a little tricky to communicate that with an electrician to do the wiring for exactly this. This is just, there's 3 states on each switch. And what finally worked after drawing many diagrams was that I said, oh, just forget that I mentioned the word relay. Just put another light switch over there, and that's then the wires I tapped into. This is a clickable interface, and what you can see there is like 2 rules that basically are combined together in an OR fashion. So if the amperage of another fan is less than 7 amps, assume the fan has failed. Or if the temperature is over a certain threshold, turn another fan on. And you could always do this before with what is called a transfer switch. You might be familiar with them for data centers. When the power fails, the UPS takes over and then starts a generator. Well, that's a transfer switch. They are an amazing piece of technology, but they're also expensive and difficult to deploy. And then if you want to do things like this, combine a transfer switch with a thermostat, essentially, it becomes very tricky. And it is tricky on a technical level, but it is also tricky on a cultural level. you would have to get your electricians and your HVAC people to talk to each other and like kind of have the same vision about how this should work. And we found this to be very difficult. In my experience, it was easier to talk to electricians. With HVAC people, there seemed to be, and we dealt with several companies, there seems to be a cultural lack of willing to hack or improvise. So we were told you can only heat a building or cool a building, but you can't just run the fan. And we came up with like a car analogy, obviously. It's like, well, in my car, I can just turn the fan on. I don't have to turn the AC on. And we were told, no, you cannot do that to a building. It does not work. In the end, we just found a way to turn furnaces on and off and keep the fans running independently. So once you have a bunch of sensors, now you can correlate events together. In this case, what you see on the top is the temperature graphs in Fahrenheit, so it was getting hot. In the middle, you see which fans were on and off, so that's like a 1 and 0. And then on the bottom, there's an airflow. Now, the airflow looks a little inversed here because there's a natural airflow, and then when the fans kick in, it actually blows them in a different direction. But what you can see both in real time and later when you try to reconstruct what happened is like, okay, it rose to a certain level, then the fan kicked in, and then things happened, it got cooler and so forth. So the interesting thing is you get more confidence in the system, how it works, as you have more data inputs, right? So you can measure current, you can measure airflow, you can measure temperature, and the picture gets more consistent. We try to anticipate the next outage and come up with rules that anticipate how that outage might look like. But you might not be able to catch them all, but at least you can go back in time and reconstruct what had happened before. This is an example of an existing alarm system that we found in one of the buildings that we bought. And I opened it and thought, oh my God, it's the 1980s. So I closed it up immediately, went home, slept over, and went back the next day. So what you see there is dozens and dozens of sensors ranging from door sensors to motion sensors to light beams and other things. And this is wired together in a certain way. They are not all these sensors are the same. And the logic is kind of encoded in how it's wired. So for instance, if the alarm is on and the door gets opened, that is a fault. The sirens go off, the security company gets called. If a single motion sensor on the inside is tripped, the assumption is it's the cat, so no alarm is triggered. But if two are tripped, the assumption is, oh, there's a break-in, right? If you upgrade your warehouse from 1 cat to 2 cats, you now have to rewire this. Would be easier to do in software, but I felt a little daunted by the prospect of doing all of that. So in the end, I decided, well, there is a siren. Let me just tap into the siren. So when the siren comes on, that's a 24-volt signal. I measure that, and then I can translate that. So if the siren goes off in one warehouse, I get an email, but I can also like trigger a siren in a different building. So you have one thing, and then you trigger something in a remote thing. And all of this has been possible. Obviously, the security companies get remote alerts, but now it's a little sensor, and you send it over an existing Wi-Fi network. So what did we get out of that? Well, we have situational awareness over our data center from remote and weekends when nobody needs to be there. We can combine the inputs from a variety of sensors that are very different, and the way these sensors inform the system is now all in software. So it is rules-based with a clickable interface. We did not disenfranchise the local people. They can still override everything. This has been proven very helpful. Like they need to do maintenance, they just turn it off, or they just see it is too hot because something changed, something was unanticipated, so they can change that. A an unexpected benefit was we were able to balance the power better across different phases. Beforehand, this was guesswork by our electricians to like say, okay, yeah, this outlet has these 2 phases in it, and so forth. And now we know exactly, okay, this is the lowest phase, so the next rack will be on that phase, and that has allowed us to stay way below the line where breaker trips. The end result is that we have 2.5 data centers without air conditioning. Now, this might not work everywhere. Our data centers are in the San Francisco Bay Area. The one in San Francisco is the coolest because of the weather pattern. This works 49 weeks out of the year very well. There are some weeks when San Francisco actually has warm weather, then it becomes a little tricky. And the way we solve that mostly is by blowing more air and faster, right? Airflow has a certain capacity for thermal to take on, and the faster you blow the air, the more you can do it. So it's not 100% a win, but it does work. In our headquarters in the former church, we are also having a big office, and we are using the excess heat from the data center to heat the building. So we think we're industry leading with that, with a PUE of less than 1, but it is also not a complete success story. It turns out that on a regular furnace, you heat the air a lot, so you can move it around. If your air is moderately hot, and by that I mean 110, 120 Fahrenheit on the hot side, the amount of energy you need to move that moderately hot air around is very high. So we reach a state where sometimes it's just easier to put a space heater in place instead of spending more energy just to force moderately hot air around. And the number that we are the proudest of is that we know how much energy it costs to store a petabyte. So currently that is 3.3 kilowatts per petabyte. I'm trying to start a meme here, so please ask your storage vendors what that number is. I just want them to get thinking about that. It would be possible to save even more. One of the challenges there that every server comes with tiny power supplies that have these tiny whining fans, and if they had bigger power supplies with bigger fans, we could push that number down even further. So it's a kind of new world. Things are easier, cheaper, and funner than they were before. The big breakthrough is that software is replacing hardware, or at least making simpler hardware and combining them in a more flexible way than it was before. And there's a potential for a lot of savings through what I call layer violations, right? So normally you figure out what your peak usage is, you tell your electricians, and they build it out for the peak usage, and you tell your HVAC people also what the peak is, and everybody adds 20%, and so you end up with a data center traditionally where the air conditioning runs to anticipate the peak. And if you at least inform these different layers with each other, you can do things like move compute jobs to run at night and increase efficiency in that way. So lastly, I want to make a small pitch. We want to expand our television recording. So if any of you want to work with us, especially in the television markets of Chicago, Washington, D.C., or Ohio, we would love to grab your local news and your local campaign ads for the next elections. Thank you.